Welcome back, everyone. In this video, I will be finishing the section on maximum and minimum values. Now, what our main focus in this section was to be able to build up to find those absolute extrema, meaning the absolute maximum and absolute minimum of a function on some closed interval. And what I'm going to start by doing here, we've already outlined what is going on above, so I just want to outline these steps before we work our problem. We want to find the absolute extrema on a closed interval a comma b. Well, when you do that, and it does have to be on a closed interval, so this, what we're about to describe, would not work if it was not on a closed interval. But if you want the absolute value on a closed interval a to b, you do the following. The first step, and this is really going to be the main step, is to find all the critical numbers. But you don't care about all the critical numbers in general, just all the critical numbers between a and b. So I'll talk about it more specifically below, but just as a general example, if you have a function that you want to find the absolute extrema on from 0 to 1, well, if you have a critical number of 1/2, you would use it because it's between them. If you have a critical number of 10, it's not relevant at all because it's not between 0 and 1. So we're going to find all the critical numbers between a and b. Once you do that, then that's actually pretty much the main step. Then what you do is you plug in all the critical numbers found in the previous step. So from part 1, along with a and b, so the numbers here, into the original function, I'll just call f of x. And when we do that for each one, we know you plug in a number, you get out a number for a function. The largest of all of these numbers, the largest is the absolute maximum. And then the smallest is the absolute minimum. And once we finish our example, I'll show you the graph of our example. And that way we can sort of explain why this works. But ultimately what's happening is when you have a closed interval and your function is continuous, so that's going to be an added step, but we're going to need that. So let's just go ahead and write f must be continuous on that interval a to b for this to work. But what's going to happen is that because it's continuous, because your graph is all connected, the critical numbers are going to tell you where you potentially turn around, like from going up to down or down to up. And what's happening at the endpoints is those turnaround points we could miss or get past them if we go on far enough. So an example, just a quick little graph here. Let's say you have a function that starts off down here. It goes up for a little bit, then it goes way down, and it comes back up to right there. Well, actually, this is not the best example. Let me redraw that so I can explain better what I want to do, what I want to say. So let's say we have a function that starts here, goes up for a little bit, goes way down, and then way back up to here. And that's the only part of the graph we're caring about. Well, the absolute minimum would be right here, which is at a critical value because it's a local minimum. But it's also coincidentally the absolute minimum because it's the smallest y value on the graph. But the absolute maximum, the largest y value, or the highest the graph goes, is all the way up here. And that's at an endpoint. So whenever you have critical numbers, it could be a turning point which coincides with the absolute minimum. So a local could be also absolute. But there might be points on the graph that never get as high up or as far down as the endpoint, so you can have the absolute maximum or minimum at the endpoints as well. Right. Now, I do want to mention that the example we're doing here, just like with the examples in the previous section, are really more typically of the more challenging aspects. But if you follow these 3 guidelines, most examples are going to be much quicker than what I'm about to show you. But the important thing about calculus, as we've gone through in every section and every idea, is that you think of things generally. You think of the steps to take. You don't think of a function specifically. So for this one, it says find the absolute maximum and minimum values of f of theta equals 2 cosine of theta plus sine of 2 theta on the interval 0, pi over 2. Well, one thing is that sine and cosine are both continuous, which means if we add them, it's still continuous. So we already have the continuity thing taken care of. We don't have to worry about, do our critical numbers work? Everything is fine. F is continuous. Now, really, we only care if it's continuous on this interval from 0 to pi over 2. So we're not going to, necessarily speak specifically about this, but it is continuous everywhere, so it's continuous here. All right, now what do we want to do? We need the critical values of this function. All right, but before I start computing the derivative, one thing I want you to think about is when you do the derivative of cosine of theta, it's just going to be negative sine of theta, but the point is you have theta inside. When you do the derivative of sine of 2 theta, the chain rule says that the inside is still going to be 2 theta. And when we have to solve equations with trig functions, we need all the inside angles to be the same. So really the first step here is actually to make all the angles the same by using the identities. And I'll go ahead and remind you of the one we're going to use here. So first we're simplifying f because it's not really in a way we're going to be able to work with it. We want all the angles to be just theta, so I'm going to have 2 cosine of theta is fine. Now the identity, the double angle identity for sine is 2 sine of theta cosine of theta. Okay, that is the double angle identity, and if you're not familiar with it or you don't remember it, the double angle identities along with the half angle identities and the Pythagorean identities are the main identities from trig that you will see pop up. All right, so we have our function we plugged in. It is sort of simplified, but we can go a little bit further before we do the derivative because there's a 2 and a cosine theta in common. We can actually factor this out. So let's go ahead and do that. Factor out the 2 cosine of theta. And what are we left with? Well, in the first function, we factor out the whole thing, so we're left with 1. And in the second part, we factored out everything but the sine of theta. All right, now keep in mind, once again, we've done one thing here, which is simplify. We haven't done the derivative, so we're not setting this equal to 0. All we've done is simplify. Now let's do the derivative. So f prime of theta. Well, to do the derivative of this, we know we'll need the product rule. The derivative of cosine is negative sine, so the derivative of the first is negative 2 sine of theta times the second, 1 plus sine of theta, plus the first, plus 2 cosine of theta, times the derivative of the second. Well, the derivative of 1 is 0, and the derivative of sine of theta is just cosine of theta. So it's just cosine of theta, the derivative of the second. Now let's go ahead and simplify. Distribute the minus 2 sine of theta through, you get minus 2 sine of theta minus 2 sine squared of theta, and then plus 2 cosine squared of theta. Okay. Now, just thinking forward, we need to solve this for theta. And what you should have learned in a trig course about solving trig equations is that it's pretty hard to solve them unless if you have the same angle inside, which we've satisfied, but also only the same trig function. We have sines and cosines, and we need just one of them. Well, for this one, because I have just a sine of theta, I'm going to switch cosine squared of theta to sine squared of theta using a Pythagorean identity. So plug in because we need only sine. And remember the Pythagorean identity, it's cosine squared plus sine squared is 1. If you solve it for cosine squared of theta, you get 1 minus sine squared of theta. All right, so let's go ahead and plug that in. Once again, this one's pretty much doing a lot of work just to be able to find the critical values. We've got negative 2 sine of theta minus 2 sine squared of theta, and then plus 2, and in place of cosine squared of theta, we have 1 minus sine squared of theta. Now, it looks pretty messy, but when you go through and simplify this now, we have, I'm going to do it in order of the powers of sine of theta. So we have sine squared and sine squared here. Well, this is minus 2 of them, and then another minus 2 of them because the 2 would be distributed. So you get minus 4 sine squared of theta. And then for just the sine of theta, you have just this term, so minus 2 sine of theta. And then for just the numbers, you have 2 distributed to the 1 would be a plus 2. And I promise one more step, and then we can actually find the critical values. And that is, because the sine squared, I pretty much always want the number on a sine squared or a cosine squared or x squared, whatever your square part is, to be positive. So I'm going to factor out at the negative sign, but I can also factor out a 2. So I'm going to factor out a negative 2 from all these. So we get negative 2. Actually, let me do it below. Equals, let me use a darker color here. We got negative 2 parentheses. When you take the negative 2 out, you get 2 sine squared of theta. And then take the negative 2 out of here, you get plus sine of theta. And when you take the negative 2 out of positive 2, you get negative 1. Well, I'm just going to keep going because I know if I'm going to just set this equal to 0 and solve it, which means I should factor this. And if you're not familiar with factoring with trig functions like sine or cosine, just pretend sine was x for a second. You would have x 2x squared plus x minus 1. Well, to set up factoring this, you would have 2 sine of theta in one of them and sine of theta in the other. Now, because it's just 2, I know it has to be set up like this. And I actually know that the last 2 numbers both have to be a 1, because if I need 2 numbers that multiply to negative 1, one's got to be positive, one's got to be negative 1. It's just up to you to make sure which one is plus and which one is minus. And the plus goes on this one because when we FOIL it out, I'm not going to go through and FOIL it out to check, but the 2 sine of theta would go with the plus 1. The minus 1 would go with the sine of theta, and that would give us a plus 1. But you can check by FOILing it out that this works. All right, now, once again, finding the critical values is the main step, because after we figure out the critical values, we just plug them in and compare the numbers we get. Well, we've done the derivative. Doesn't really seem like we've done anything new since, pretty much maybe like 8 sections ago when we started talking about trig derivatives. But we can go ahead and do the critical values now. So I'm going to actually use this as my final simplified derivative. And then to get the critical values, we take our derivative, negative 2, parentheses 2 sine of theta minus 1, times cosine of theta plus 1. Or sorry, that's a sine of theta, not cosine of theta. Times sine of theta plus 1 equals 0. So I'm taking my derivative, setting it equal to 0. Keep in mind we have no fraction here, so this is the only equation we have to solve. And we also talked at the beginning that f is continuous. So when we get theta values here, we're just done. We don't need to check anything else. Well, in order to solve this, I set each part to 0. The negative 2 doesn't matter, so I just have 2 sine of theta minus 1 equals 0. And the sine of theta plus 1 equals 0. Now, if you solve this for sine of theta by adding the 1 and dividing by the 2, you get sine of theta equals 1/2. And what I want to point out here is the interval we're given is quadrant 1. If you're thinking about the unit circle, 0 to pi over 2. What angle in quadrant 1 is sine 1/2? Well, that's actually pi over 6. So we have one answer for here as far as critical values go. Now the other one, to solve this, we would subtract 1 and we get sine of theta equals negative 1. But what do we know about sine in quadrant 1? It's positive. Well, it starts off at 0, but it's all positive. So it's never negative 1, which means this is not a critical value, at least in our interval. Yes, sine of theta does equal negative 1. The angle you can think about is 3 pi over 2, but it's not in our interval, so we don't care about it. It's not a critical value for us, for our problem here. All right, so the way to think about what we just did is we did all that work, but we figured out the one critical value, which is pi over 6. Well, now, what do we do with that? Just scrolling back up, we plug in the critical numbers. And I apologize if I use critical numbers or values. I think I talked about before, they mean the same thing. But we plug in pi over 6 along with a and b. A is 0 and b is pi over 2 the endpoints. We're going to plug in these three numbers into our original function and then just compare to see which one goes with which. All right, so I'm going to make a little xy chart here, or theta and f of theta. And we're going to plug in 0. We're going to plug in pi over 2. And we're going to plug in pi over 6. All right, and this is a point where if you don't remember the unit circle, you really got to know it, because we want the exact values. I don't want to see decimals for this sort of thing. So if I plug in 0 here, I get 2 cosine of 0, which is 2, plus sine of 2 times the angle 0, that's still 0. Sine of 0 is 0, and that's actually a 0. So when we plug in 0, you get 2. Now we have to plug in all the rest to know which one's the absolute maximum, which one's the absolute minimum. Now for pi over 2, cosine of pi over 2 is 0, which means the first part is 0. Sine of pi over 2 isn't really relevant because we have to multiply it by 2, but if we plug in theta equals pi over 2, our angle is pi, and sine of pi is also 0. And, you know, if you wanted to check, you could plug this in your calculator, you'll get some decimals, but with whole numbers, you'll see the 2 and the 0. Now, pi over 6 is definitely the one you have to know the unit circle for. So I'm going to just plug it in very visually. We have 2 cosine of pi over 6 plus sine. And when we plug in pi over 6 here, our angle becomes 2 times that, which is pi over 3. 2 times pi over 6 is pi over 3. And now cosine of pi over 6 is the square root of 3 over 2. Sine of pi over 3 is also square root of 3 over 2. And while you might be inclined to cancel these 2's out, because they're each has square root of 3 over 2 in it, you can think about this as 2 of them plus another one of them means there's 3 of them. So this is 3 times the square root of 3 over 2. Now, once we have all these y values, 2, 0, and 3 times square root of 3 over 2, our job is to point out the smallest one, and that's the absolute minimum, the largest one, and that's the absolute maximum. Now you can probably gather here that 0 is the smallest one because both of these are positive, so 0 will be the absolute minimum. But what about the absolute maximum? If you're anything like me, you don't know roughly what 3 times square root of 3 over 2 is off the top of your head, so let's just figure that out. 3 times the square root of 3 divided by 2, and as a decimal it is bigger than 2, so this is the absolute maximum. All right, so to repeat, the biggest number here, 3 times square root of 3 over 2, out of these 3 choices is the absolute maximum, and 0, the smallest out of these 3 choices, is the absolute minimum. But when you write your answer, you're going to use the radical form here. So the absolute min equals 0, and the absolute max equals 3 times the square root of 3 over 2. Right? And that's really all there is to it. Now, as I mentioned when I started this problem that this one was going to be much harder, and it is, than your normal one because we had to use trig identities a couple times just to be able to find the critical numbers. If you have something like a polynomial here, when you do the derivative, it's just the power rule, and you end up usually factoring out the end, getting your numbers, and then plugging it in. So this step becomes a lot quicker. But this is probably about as messy as an example as I can think of, and at the end of the day, the point is follow those steps and you'll be in a good spot. Now, the last thing I wanted to do here, like I mentioned at the beginning, was graph this and show you what it looks like. So let's go ahead and do that. We got y equals 2 cosine of x plus sine of 2x. And we only care about this graph between 0 and pi over 2. Let me go ahead and switch the step size on x to pi over 2. That way we can easily see that pi over 2 is right here. And what I want to point out is that if I scroll in here, we're looking at the graph only starting from here. So at x equals 0 to x equals pi over 2. I only care about this little section. I don't care about anything else. Well, what we did without graphing this at all was we figured out that the largest y value, the absolute maximum, was 3 times square root of 3 over 2. And we typed that in already. We know that's about 2.598. You can go back and look here. And the absolute minimum is the y value of 0. And we actually figured out where they occurred as well, because the 0 came at pi over 2. The 3 times square root of 3 over 2 came from pi over 6. Right? And so just as a reminder, but the main thing is that we did something pretty impressive. And, you know, this kind of function that you're dealing with, not that it's an unrealistic or realistic type of function, but it's just very hard to deal with, because basically anytime you have to deal with trig functions and solving trig equations, you got to think about all the identities, you know, and trying to simplify them, converting everything to just sine or just cosine and everything else. So this is a very challenging problem, and we figured it out. But that's it for this section, and I will see you in the next section.